My name is Victor, and welcome back to another ALINT-PRO tutorial. In today's video, we will be covering dynamic CDC analysis of some simple synchronizers recognized by ALINT-PRO. In previous videos, we've covered ALINT-PRO's static CDC analysis capabilities, but ALINT-PRO can also generate CDC assertions to assist with verifying a design and simulation. As such, this video will utilize Riviera-PRO to simulate a test bench that includes the CDC assertions generated by ALINT-PRO. So, to get started with this design, we'll go ahead and open up the CDC Synchronizers demo workspace here in the Open CDC Example folder. So, opening this up, we notice that we have 14 projects over on the left, which are all the same projects as utilized in the static CDC analysis videos that came out before this one. Now, in order to get started, we are just going to clean our workspace, and then we can go ahead and begin with explaining how this process is going to work, and then moving on to what the 4 demo synchronizers will be for this video. So, in order to move over all of our files from these projects to a simulation in Riviera-PRO, we utilize these 2 scripts here in the bottom left. So the first that we'll be actually calling from ALINT-PRO is going to be the runme_sim.do script. So essentially what this script does is it takes in one argument, which is going to be the name of whichever project it is you want to simulate. And what it's going to do is it's going to run that project first through the static CDC analysis in the flow manager here. And it's also going to generate the project's assertions using this project generate assertions command. After that, all this script does is it figures out where you have Riviera-PRO installed, and then it takes that location and executes Riviera-PRO, and during that execution, it sends over the second do file, the Riviera_sim.do, for Riviera-PRO to execute. And so what this file does is it takes in a few arguments from the previous script and essentially creates a workspace and a design for the project that you picked out. It loads in all of the files from that project in ALINT-PRO into the design in Riviera-PRO. And then after that, it goes ahead and compiles all of those files and then begins our simulation. It also creates a view in the waveform viewer as well as the data flow viewer. So after that, we load up our waveform configuration file, and this just makes it look more readable than the default. And then finally, we go ahead and run the actual simulation. So if I go ahead and check what my current working directory is, you'll notice that I'm in the custom synchronizers directory. So if I want to execute this script on some other directory, let me go ahead and set that as the active one. So we'll go ahead and start with the NDFF synchronizer. So in order to execute the script for this particular project, what we want to do is we want to go ahead and go over to the console window, and we want to be in the same directory as the script itself. So I'll go ahead and move back to the previous directory, and from here I can go ahead and execute it. So I'm going to say do runme_sim.do, and we also have to provide one argument, and that argument is going to be the name of the project that we want to simulate. So if I type NDFF_sync and I run this command, we will go ahead and begin the process of running the script, and that will open up Riviera-PRO. So as you'll notice over on the left, we had the CDC assertions file generated, and so this was done by the script, and we can go ahead and take a look at that so we can see what exactly what assertions are applied to an NDFF synchronizer. So going ahead and opening that up, we can see that there are 2 different assertions here that we have to satisfy in order for our simulation to be considered correct. And so the 2 different assertions are being glitchless and for the signal to be stable for a certain amount of clock cycles. Specifically, it's for 2 clock cycles, and the signal that needs to be stable and glitchless is the data signal. So this is going to be the data input signal that is being fed into the 2D flip-flop synchronizer, or the ND flip-flop synchronizer. And the signal with which it needs to be glitchless and stable with respect to is the clock B signal. So in other words, the input or the transmitting data needs to be glitchless and stable with respect to the receiving clock domain or the other clock domain. And so this assertion has to hold in our simulation, or else we will get assertion violations. So now that we've looked at that, we can go ahead and close it and take a look at the Riviera-PRO window that has just opened. So taking a look at the Riviera-PRO window, we see a few things. First, we see over on the left the workspace and design that were created by the script, as well as in the center here, we see two different windows, one for the data flow of our design and one for the waveform. In the bottom left, we see the console. So this console detailed all of the small things that the script went through, basically including opening up the workspace or creating it, creating a new design, loading in all the files from ALINT-PRO, and then beginning the simulation and opening up the other windows. And finally, the last window here is the assertions window. And so this essentially gives us the information of how many times each assertion ended up being tested during the simulation, as well as how many times each assertion passed. So here you'll notice with this particular design and with this test bench that we haven't quite looked at yet, that each of these has been attempted at least a few hundred times, if not more, and they've passed all of those attempts. Now we can go ahead and look at the test bench, which is going to be very similar for all of these first four simple synchronizers. So, opening up this test bench, we'll go ahead and start at the top where we have 6 different parameters. And so the point of these parameters, the first two, is just to specify half of a period for each of the clocks. And these numbers are from our 8.adc file over in ALINT-PRO, where we specified that clock A had to have a period of 10 and clock B had to have a period of 16, and so these are half of those. The second two parameters are exactly as they say. The slow clock will be whichever clock is slower, and the fast clock will be whichever clock is faster. The fifth parameter essentially is going to say how many cycles we want our signal output to be stable for. So if you want it to be stable for 2 seconds, you put 2 plus 1. And then the final parameter is going to dictate how many cycles we need in order for a data change to occur to maintain 2 stable cycles. And so that's given by this formula over here. After the parameters, we have a few device under test signals that feed directly into the DUT, as well as one signal called count, which is going to be used for the test bench self-termination. And then we have the actual device under test instantiation and the CDC assertions instantiation as well. After that, we simply initialize a few internal reg signals to 0. And then we have the 2 clock generators, one for the transmitting, one for the receiving. And then we have here the data in signal stimulus, which is going to be this line here. And essentially what this is doing is you're taking whatever count is, because count gets incremented at every negative clock edge, and you're modding it by cycles per data change, and then you're going to take the knot of that. So in other words, every time the count is divisible by this cycles per data change, we're going to toggle dn. And so that's going to allow dn to change once for every time the count mod cycles per data change is 0. And the last block here is going to be the self-checking termination block, which essentially just checks once the count has reached some maximum value and then pauses our simulation. So now that we understand how the test bench is built, we can go ahead and take a look at this waveform viewer one more time. Now, once I move this cursor, the attempts are going to go away. If I move it back to this exact position, then the attempt counts and the lists of the assertions will come back. So we can go ahead and see exactly what's happening. So up at the top, we have the current count value. So at the beginning of the simulation, we have it at 0, and then this just increments by 1 for every single negative edge of clock A. And that's exactly what we expect based off of the test bench module. And now we can also take a look at the input data. So the input data here is called dn, and you'll notice that dn stays on and off for long periods of time. Or in other words, it's going to be on for many, many clock cycles of clock A. Specifically, if we compare the time in which dn is on to the clock cycles of clock B, we'll notice that DN is always on for at least 2 of clock B's cycles. So in this case, we have DN being on. So here's the first clock edge from here to here, and the second clock period. And so this DN signal is stable for that entire clock period. And you'll notice the exact same thing applies over here. Both turn on at this exact moment, stable for 1, 2, and even 3 clock cycles in this case. And so that continues on with the rest of this simulation. And every single time we get one of these changes, we essentially have another test for the DN signal being unstable or being a glitch. But if we go back to the end again once more, we'll notice that we passed every single one of these attempts for checking if there was a glitch or if there was a stability issue. And that essentially comes down to the way the test bench was designed, ensuring specifically with the parameters for making sure that the cycles per data change were very, very long. This ensured that we never had any glitches from DN to clock B or any stability issues. The rest of the test benches for the next 3 modules will be very, very similar, with the only difference being which synchronizer we are instantiating within the test bench itself. So now that we've seen this flow for the first synchronizer, the next 3 that we'll be going over will be very similar, and we'll go ahead and start with the second one. So I'll go ahead and close Riviera-PRO here. Now that I'm back into ALINT-PRO, I will go ahead and begin with the next one. So the other 3 that we'll be going over are going to be the NDFF SRL synchronizer. We're also going to be going over the wide NDFF synchronizer. And then the last one we'll be going over is the half cycle NDFF synchronizer. So we'll go ahead and do the wide D flip-flop as the second. I'll go ahead and clear my terminal here. And now that my terminal is cleared, I'll go ahead and check my working directory to make sure that I have to, and in this case I do, have to go back to the base workspace directory. So I'll go ahead and say do runme underscore sim.do, and here I want to run the wide ND flip-flop synchronizer. And so now that this is running, I can go ahead and take a look at the CDC assertions for this as well. So opening that up, here's the view. So for the wide ND flip-flop, you'll notice that we have a few more assertions than we did for the previous example. We do have the same glitchless and stability ND flip-flop assertions as we did for the ordinary ND flip-flop. However, you'll also notice this additional wide ND flip-flop assertion, which essentially says that your ND flip-flop has to be a gray code counter, or in other words, 1-bit change at a time, because otherwise you might run into some types of data coherence issues. Now below, you'll notice that in addition to having the 1-bit change assertion specified here, we also have an additional glitch, no glitch, and stable assertion for each individual bit of my wide ND flip-flop. So that's where these last 6 are coming from. So now that we've taken a look at those, we can go ahead and open up Riviera-PRO. And over here in Riviera-PRO, we see a very similar view to what we saw before. We can go ahead and open up the test bench. So I'll go ahead and close that one real quick. Open up this test bench. The parameters at the top are exactly the same as I described in the ND flip-flop synchronizer section, as are the device under test signals, with the exception of DN and DOUT being multi-bit signals. We also have a few test bench signals that are slightly different. So we still have count, but now we have gray and binary count instead. The device under test and CDC instantiations are identical, as are the internal signal initializations. And we also have the exact same clock A and clock B generators. Down here, the self-checking termination is identical, and the main difference occurs in these 2 lines. So this first line is essentially taking our binary count from the ND flip-flop and creating a gray count, or a gray code count. And so the purpose of this is to ensure that whenever we're sending a signal to the input data, that we're sending a signal that is only changing by 1 bit at a time. And so that way, we don't violate the assertion, which dictated that you can only have one bit change at a time. And so that's what this gray count and this if statement in here are doing. That's the purpose of those. Otherwise, it's exactly the same content. You still have the count incrementing by 1 at every negative clock edge of A. We can also go ahead and take a look over at the assertions viewer down here. So in the assertions viewer, you'll notice that we have all of the 9 different assertions we mentioned earlier, and they all pass every single one of their attempts. We can also take a look over at the waveform just to get an idea of what this looks like. So zooming in and going over all the way to the far left, we can go from the beginning where count starts at 0 and goes up to 1 and so on. Again, this data input is transitioning after multiple clock edges of clock A, and you'll notice that DN can only change so quickly in comparison to clock B. Again, it's stable for at least 2 of clock B's clock cycles. And so the next thing we want to check is the stability in terms of one bit being changed per cycle. And so we'll notice that, again, because we encoded this as a gray code counter, every single one of these changes only manipulates 1 bit. So here we change the bottom bit, here we change bit 1, bit 0, bit 2, and then we change bit 0 again, and so on. So we never change multiple bits simultaneously. And so this preserves, or rather allows, the assertion to not be violated. So now that we've finished up with the wide ND flip-flop synchronizer, we can go ahead and move on to the next one. So I'll go ahead and close up Riviera-PRO. No need to save any of the changes to the waveform. Now we can begin on our third synchronizer. So we just finished the wide D flip-flop, and we already did the ND flip-flop. So now we can go ahead and move on to the third one. So I'll go ahead and do the half-cycle ND flip-flop. So on the half-cycle ND flip-flop, we can go ahead and do the exact same process as before. Clear the terminal, check my working directory. So I am going to have to go back a workspace here, run my_sim.do, and then I want to execute half-cycle ND flip-flop synchronizer. So running this, I can go ahead and close this CDC assertions tab and open up this one instead. And so I can take a look at the differences between what this one is and what the ND flip-flop synchronizer had. And there aren't many differences. In fact, they are exactly the same. The main difference between these two implementations at all is simply that you have the positive edge and the negative edge of the cycles feeding into whatever your ND flip-flop synchronizer is. So that's the real difference between the two implementations. So if we were to go and take a look over at the Riviera-PRO executable, we can see that we have this almost done running, and once it's finished running through the script, the data flow and the waveform tabs open up, just like in the previous examples. We can also see in the bottom right that the pass counts are almost identical to what we saw before, because we have the exact same amount of time run, because our count in our test bench runs for the exact same amount of time. So if we open up this test bench, we'll notice almost every single parameter is the same. The DUT signals, the test bench signals, the instantiations are all the same. The clock generation signals are all the same, as well as the initializations. And essentially everything works exactly the same in this test bench. And so we get a very similar picture in terms of the waveform. And if we go over to the beginning, the only real difference is that if we take a look at the time it takes from DN going to the output, which is going to be over here stable, we'll notice that it only takes 1 and then 2 clock cycles, or rather 1 or 2 transitions. Because instead of having to go through 2 full flip-flops, where each reads in on the positive edge, we instead read in on the positive and the negative edge. So the first is the positive, then the second is the negative. And so that means it can go through twice as quickly. So that's the main difference here. Other than that, there is functionally no difference, certainly no difference in terms of the test bench, no difference in terms of the assertions, and very minor differences in terms of the waveform itself. So we can go ahead and stop with this synchronizer, and now we can go ahead and move on to the last synchronizer. So I'll go ahead and close up Riviera-PRO now. And then once I'm back in ALINT-PRO, I can do exactly the same thing I did before. So here, I want to go ahead and work on the last one, which is the NDFF SRL synchronizer. So go ahead and check my working directory. I do have to go back here. So I'm going to say do, back to the previous directory, run me sim.do, and I want to do the NDFF SRL synchronizer. So once I go ahead and execute this, it should begin the script again and put it over to Riviera-PRO. We'll go ahead and close this CDC assertions and open up the next one. And so we can go ahead and take a look at this again, but it is the exact same thing we've seen twice already, which is the same for the NDFF synchronizer and for the one we just went over. So now that the test bench has finished executing, we can go ahead and take a look at its contents. So we can see this is our old test bench. If we open up our new one for the SRL synchronizer, the exact same parameters at the top, same device under test, same test bench, same instantiations, similar internal signal initializations. The only difference here is that these two signals are multiple bits, but the idea remains the same. You initialize them all to 0. The clock generators are the same. The self-checking termination is the same, as is the data and signal stimulus. So the test bench is nearly identical, with the only difference being the initialization signals. And if we were to take a look at the waveform, we will get a slightly different waveform here. And the reason why is because this SRL synchronizer is not a 2D flip-flop synchronizer, like in the previous examples, but rather it is a 5D flip-flop synchronizer. We still have the same pass counts down in the bottom right for the assertions tab, but we do have the SRL register signal here, essentially delaying our signals multiple clock cycles. But other than the fact that we have more registers for our synchronizer, the concept is exactly identical to the ND flip-flop synchronizer we did at the very beginning, but instead of 2, we now have 5. So that'll be it for today's video. Thank you for watching.